Hello there, Mr. Sutton here, bringing you the AB Calculus 5-9 Extra Practice Number 1 solutions on FTC Graphical Analysis. For this problem, we've got a graph of f shown here, and we have this function g that's the integral of f from a to, well, whatever. So we want to know for what value of x does g of x have a maximum. So normally you would run the candidates test. That's a little tough on this one though, because we just have a bunch of letters to work with. So we kind of have to understand the theory behind all this. And the only thing we really have to go on is this graph, specifically the sign of f in this graph. So where that's going to help us out is we can at least make the connection that g prime equals f of x. So this is the graph of the derivative of g. And if you're trying to figure out where g has a maximum, we can take a look at where the sign of g prime is changing from positive to negative. In this graph, we see that g prime is positive, greater than 0, on the interval from a to c. And it's negative on the interval from c to d. What this means is that the original g function is increasing from a to c. And then it's going to be decreasing after that. So if you have a quantity that's increasing between a and c, and then decreases, and that's all it does for all its lifespan, well, that means that the maximum value must occur at c when we stopped increasing and started decreasing. So that means we have answer choice C for this one. On this problem, we've got some function f, and we also have this other function g that is the integral of f from 0 to 2 times x. So that's kind of interesting in there. Based off of this, we want the value of g prime of 3. So let's start by finding the value of g prime of x. Using our first fundamental theorem of calculus, if we have a variable in the upper limit, we essentially just replace t here with that upper limit and then multiply by the tail. So this is going to be f of 2x times 2, because the derivative of 2x is 2. All right, so now we need to do g prime of 3. So that's going to be 2 times f of 2 times 3. So that's 2 times f of 6. F of 6 right here, that's the y value at 6, so that's negative 1, more or less. So we've got 2 times negative 1, which is just negative 2, which gives us answer choice C. On this problem, we're given the graph of g of x up here, which is the integral of some f function, and we essentially want to figure out which f function down here could give us this when we take the integral. So the key relationship here, and you'll see this if you do fundamental theorem on this and replace the t's with x's, g prime of x and f of x are the same thing. So you're saying that the graph of f down here is the derivative of g, which we kind of already knew looking at this, but now we've got an official confirmation. All right, so what is g doing? And then that'll help us figure out what f is doing. G starts by increasing, turning around, and then decreasing. So what does that mean for g prime? Well, that means that g prime starts out positive, and then if we're turning around, g prime must be going to 0, and then if we're decreasing, g prime is going to be negative. So which function mimics this behavior here? Well, this first one, we're starting positive, we're 0, we're negative, but then this thing goes to 0 and positive again. And that's not what this graph up here calls for between A and B. So choice A is no good. For choice B, we're not even starting positive, that's out. Choice C, we're positive, 0, then negative, so maybe. Choice D, we're positive everywhere, so no way. And E, we're negative to start with, so that's also bad news. So then by process of elimination, choice C is our best answer. For this problem, they're asking us to find for what value of b between 0 and 2 is this integral from 0 to b at a minimum. Now, since they gave you things to plug in, you could just plug all these into b on the calculator and see which one gives you the smallest number. But if you wanted to do it a little bit more methodically, we could use the candidates test. So first off, I'm going to let this expression equal f of b, just so I have something to quickly refer to it. And since I'm eventually going to have to test things in this function, I'm going to put it in my calculator now. So here's what I've entered in my y equals on my calculator. I've got the integral from 0 to x of cosine of e to the x dx. Now, just a couple differences from what we wrote here. I have to put an x up here in this integral because that's the input, and that's the only variable your calculator accepts as an input with the y equals. And if I really wanted to be mathematically accurate, or at least technically accurate, I would use another letter like A or B instead of X in here. But your calculator actually doesn't mind if you use the same variable up here and also over here. It somehow figures that out. All right, so we're going to plug things into this function eventually. But what are we plugging in? So definitely we have to plug in the endpoints of 0 and 2. Those always need to be tested. But we also need to plug in critical values. So to find critical values, I need the derivative of this f function that I just kind of created, which is just going to be cosine of e to the b, right? If you're taking the derivative of something with a variable in the upper limit, just plug in the variable and multiply by a tail if there is one. So there's what I'm actually going to graph to see where this crosses the x-axis. And by crossings, I'm really just looking for places where I'm going from negative to positive because I'm just looking for a minimum. So here I am back on the calculator. I've put in this cosine of e to the b, which I have to use x instead of b on the calculator. I'm going to unselect this function up here because I don't want to graph that. And I'm also going to go to Window to make my life easier. And I'm going to make my interval from 0 to 2 because that's the only places that we need to look based on what the problem just told us. All right, so let's do zoom and then 0, zoom fit, to see what this derivative looks like. So here we go. So it looks like we're crossing in just 2 places. Now again, I don't really need to test both these places. This first one right here, we're going from positive to negative derivative. So this is a local max. There's no way a local max is going to be the absolute minimum of a function because it's higher than all the things that are nearby. So we're just going to look at this one over here. So I'm going to do second and trace in order to get this 0 function here. And let's see, let me move my spider a little bit closer, press enter, move it past the 0, press enter again, enter one more time, and that is the value 1.55 and some change here. So this is the only value that we actually need to test out on here other than 0 and 2. And to make my life a little bit easier, I'm going to go back to the calculator, I'm going to quit out of my graph, and I'm going to press the store button to immediately store that value as A, or whatever letter you want. Now I don't have to retype the whole thing. Okay. At this point, we're going to go ahead and test the endpoints 0 and 2, and also this thing that I just stored as A or B or whatever you want to store it as. So at 0, I actually don't need to plug that in my calculator because it's an empty integral, so that's just going to come out to 0. But I am going to have to test out f of this 1.55 number. So going back here, I'm going to go to alpha trace to pull up my y equals menu, and I stored the original function in y1. So I'm going to press enter on that, and for my input, I'm going to do alpha a, or wherever you stored that variable, that number, and that comes out to negative 0.5358 and some change. So far, that is going to be our min. But let's keep going. Let's test out 2. Now, logically speaking, you've been decreasing up until this spot right here, and you're only increasing afterwards because you've got this positive area. So there's really no way that 2 is going to give you a lower number. But just for the sake of argument, let's just go ahead and plug it in just to be thorough. And we see here that, not surprisingly, we come out with something that's higher than the number we just got because we've added that positive area. So looking at all those, our min then happens at x equals 1.550, which is answer choice D. For this problem, we're given the graph of f, and we want to figure out the graph of g, given that f is the integral from 2 to x of g. So for this one, the key on this is realizing that if you take the derivative of both sides here and use your fundamental theorem, f prime and g of x are the same thing. So if we're looking for the graph of g, we're essentially asking for a graph that gives us the derivative of this graph up here that they gave us. So the f function, you'll notice, is just an increasing line. That's it. That means that the derivative of this thing, since it's increasing, it's going to be positive. So that already rules out some of these answer choices. But also, since it's just a line, it's going to have a constant slope. So we're looking for the graph of a positive constant. And that means we just have a horizontal line above the x-axis, which means answer choice A is what we're looking for. On this problem, we're given the graph of f, and g is defined as the integral from 0 to x of f. Based off of that, which of the following is an equation of the line tangent to the graph of g at x equals 5? So if we're asking for a tangent line for the graph of g, which they haven't shown us, we're essentially asking for a line that goes through g at a certain point and has the derivative of g prime of 5. So we need to figure out g prime. Well, if g is this integral here, g prime of x is just going to be f of x using our fundamental theorem. So let's start by figuring out what g prime of 5 is, because that's going to give us the slope for our tangent line. G prime of 5 is just f of 5, and f of 5 we can just look up on this graph here. At the x value 5, the f graph has a value of -1. All right, let's keep going. In addition to our slope, we also need a point that our graph goes through, which means we need an x and a y value. We've got the x value already. They gave it to us. It's 5. We need the y value that goes with 5. To figure this out, we need to figure out g of 5. So that's basically asking for the integral from 0 to 5 of my f function here. So I'm going from 0 all the way to 5. I'm just asking about area under the curve. So let me shade all the area that we care about here. And we've got actually 3 different shapes that we're going to have to use the area for. We've got this trapezoid. We've also got a triangle from 2 to 4 here. And then this last little piece, we're going to have to use a trapezoid to find that. So going through one at a time, let me start with this trapezoid. So I'm going to have my bases of 1 plus 2 all over 2 times a height of 1. Next, I've got this triangle. So that's going to be, and it's under the x-axis as we move to the right. So this is actually negative area down here from here on out. So this is going to be minus 1/2 times a base of 2 times a height of 2. And then finally, we've got this trapezoid, another negative. This is going to be minus, and now I have bases of 2 plus 1 over 2 times a height of 1. And I'm going to have to actually add all this up because these are multiple choice answers here. So going through, it looks like this trapezoid and this trapezoid are actually the same exact area if you really analyze what you're doing there. So really, it's just this negative triangle that ends up counting at the end. This is going to be, let's see, -1 times 2, which gives me -2. So what do we do to put this all together? Well, I'm going to use point slope form. Y minus y1 equals m times x minus x1. And if you look at the answer choices, they are all actually in this form to begin with. So my y1 here, that's going to be the y value that I just found. So I'm going to write y minus -2 or y plus 2 equals the m value, that's this g prime slope that I just found of -1, times x minus this x value they gave us of 5. So altogether, it looks like that's going to give us answer choice E. For this problem, we're given this f graph and this g function that's the integral from 2 to x of the f graph. Based on that, we want the value of g of 10 times g prime of 10. So this is 2 different things that we need to find and then multiply together at the end. So let's start with g of 10. So that's the integral from 2 to 10 of f of t dt. So that's essentially the area under the curve between x equals 2 and x equals 10. To find that area, I'm going to need to use a few different shapes. From 2 to 6, I can use a big trapezoid. And then from, let's see, 6 to 8, I can use a triangle. And then from 8 to 10, I'm going to need a trapezoid for that. Unfortunately, we're not going all the way to 12. Otherwise, we could have used one big triangle under here. All right, so let's go from left to right and find those areas. First area is above the x-axis as we move to the right. So this is going to be positive. So this is going to be, using my trapezoid formula, a base of 1 plus a base of 4 over 2 times a height of 3. And next, this triangle, this is under the x-axis as we move to the right, so this is a negative triangle area. So I'll have minus 1/2 times a base of 2 times a height of 2. And then this last trapezoid also negative because it's under the x-axis moving to the right. So this is going to be a base of 2 plus 1 over 2 times a height of 2. And now we have to add it all together. So let's see here. I've got, this is going to be, let's see, 5 times 3 is 15 over 2. This is, here we're just subtracting 1 essentially, no, subtracting 2. So 15 over 2 minus 2, that's going to be, let's see, we're subtracting 4 over 2, so that's 11 over 2. Over here, we're subtracting 6 over 2. So that's altogether 5 over 2, just a lot of math there, a lot of arithmetic. Now for the easier one, g prime of 10. Since g equals the integral of f, using our fundamental theorem, we can say g prime equals f of x. So that means g prime of 10 equals f of 10. F of 10 is just the y value with the x value 10 on this graph. So down here, that's negative 1. All right, so now g prime, or g times g prime of 10, that's going to be the 5/2 for g of 10 and the negative 1 for g prime of 10. So altogether, that comes out to negative 5/2, which gives us answer choice C. On this problem, we're given the f graph here from negative 2 to 2, and g is the integral of f from 0 to x. So you got to pay actually close attention to the lower limit of integration on this problem, because on this one, they want to know on what open interval is g negative and decreasing. Let's start with the low-hanging fruit and talk about where g is decreasing. For that, we need to know a little bit about g prime, and since this is our g function, g prime, using our fundamental theorem, is just going to be f of x. And so if we're asking where g is decreasing, we're asking where g prime is negative. G prime, aka f, is negative wherever this line is negative, so that's between negative 2 and 1. So because g prime is negative down there, that means our g function is decreasing on that interval. And that's one of the answer choices. However, we have a little bit more to consider, because we also want to know the interval where g is negative. This is the original function now needs to also be negative in addition to decreasing. So for that, we have to look at the original function, and this original function is basically adding up the area under the f curve. So the area from negative 2 to 0, this is below the x-axis, so this area, since it's under the x-axis, would normally be counted as negative area. However, if you look at how the g function is set up, we are integrating from 0 to whatever the input is. So that means if you're trying to integrate this area, you're essentially starting here and going backwards. Since we're integrating this backwards, integrating negative area backwards makes it positive, and that's not going to count towards our answer. It turns out that only this area between 0 and 1, which is negative because it's under the x-axis, and because we're integrating from left to right at that point, this is the only negative area for this problem. Since only that area from 0 to 1 is negative, that means it actually is going to be answer choice C, not B. For this problem, we're given the graph of f and this g function, which is the integral of f, and we're trying to maximize this g function. So however you're going to do this, you're going to need to find critical values for g. So for that, we need g prime, which using our fundamental theorem we see is actually just f of x. And now there's two ways you could go from here. One is you could figure out the critical values and test those along with the endpoints in the g function, basically the candidates test, to see what gives you the biggest value. And there's a lot of merit to this approach. They want the maximum value anyway, so you're going to need to plug something into g at some point. Another way to do this, though, to find the best x value, is to use the lonely critical value test. Basically, looking at the g prime function, which is just this f function here, we see there's only one critical value on this whole interval, and it's a local max. We're going from positive to negative. So because g prime is greater than 0, positive between 0 and 3, and it's also less than 0, negative from 3 onwards, since essentially g is increasing until it gets to this spot and then decreasing afterwards, that means whatever the value of g is at x equals 3, that has to be our absolute max. So once we've reasoned this out, actually, all we have to do is plug 3 into the g function here. So we're just essentially finding the integral from 2 to 3 of the f function. So going from 2 to 3, we just have this one little triangle to compute. It's positive area because it's above the x-axis moving to the right. So that's going to be positive 1/2 times a base of 1 times a height of 2. Half and 2 cancel, leaving us with just 1, which gives us answer choice B. For this problem, we're given the graph of f up here between -2 and 2, and we're asking which of the following could be an antiderivative of f. So we're given f, we're looking for kind of big F, I guess you could think of it as. Now the thing I always look for with these derivatives is I look for critical values, specifically places where my derivative graph up here is crossing the x-axis, because those are going to give me smooth turnarounds, either local mins or maxes, down below here. So looking here, we cross the x-axis in 2 places. Since I have 2 x-intercepts, crosses actually, not just like bounces, like we're crossing through, that means we're going to have 2 smooth turnarounds for the antiderivative function. So let's see what we can eliminate based just off of that. Choice A has 1, 2, 3 smooth turnarounds, so that can't be it. B has more, that can't be it. C has a bunch of smooth turnarounds too, more than 2, 4 to be precise. So it looks like actually only choice D has 2 smooth turnarounds. And if you really just wanted to confirm, it looks like we are having a positive derivative between -1.5 and positive 1.5. And on this graph, we are increasing on that interval for the antiderivative. So that all matches. Choice D then is our answer. For this problem, we're going to be using this graph here for the next several parts. So we've got some function on the interval from -5 to 4, and this is the f function. The g function is based off of that. It's the integral of this function between -3 and x, which is kind of a weird place to start, but hey, I didn't write the problem. So we've got g of 3 that we're trying to find in the very beginning. For this, all we have to do is plug 3 in here. So the integral from -3 to 3 of the f function, essentially the area under the curve of f. So from -3 to 3, we have a couple shapes we're going to be using. From -3 to 0, we've got a triangle, a positive triangle. And actually, we can go a little bit further. We can go all the way from -3 to 2. This is all just one big triangle here. So we're going to have positive 1/2 times a base of 5 times a height of 4. And now, to get all the way to 3, we actually just need to go one more here. This is going to be a negative triangle. We're going to have -1/2 times a base of 1 times a height of, you can actually read it right off the graph here, that's 2. And we don't actually have to simplify this, but I'm going to anyway, just in case we need it later on. But if this is the AP test, you would wait until you needed it later to actually go ahead and simplify it on that problem part. But going ahead and simplifying this, we've got essentially, let's see, half of 4 is 2, times 5 is 10. Over here, this all just comes out to 1, so 10 minus 1 should be 9. For this one, we're trying to figure out the open intervals between -5 and 4, where the graph of g is both increasing and concave down, and justify the answer. Let's deal with increasing first. If we want to know where g is increasing, we need to know where g prime is positive. Since g is this integral function, g prime, using my fundamental theorem, is just going to be f of x. So essentially this graph up here. And we see that this graph is going to be positive from -5, so we want positive now, from -5 to -3, and also from -3 to 2. So that means that the g function is increasing on these intervals. Now, you might also say that the g function is increasing at -3 exactly, and that's one of those debatable things where do you include these border values or not? But the way the AP test is structured, that's not going to end up affecting your final answer. Right now, it looks like it could affect it, whether or not we include this -3, but you'll see that it doesn't. Keep going here. So for concave down now, we need to know where g prime, which again is this graph, is decreasing. So this graph is only decreasing from -5 to -3, and also from 0 to 2. At least those are the only intervals in this this sub-interval that are decreasing. So of these intervals, g prime is decreasing from -5 to -3 and 0 to 2. Therefore, it is only on the intervals from -5 to -3 and 0 to 2 that g is increasing in concave down. So see, it didn't actually end up mattering whether or not we included this -3 as being on an increasing interval because it was not on a concave down interval. On this problem, the function h is defined as g of x over 5x. Based off of that, we want h prime of 3. So let's take the derivative of h to start with here. Since we've got one function over another, we're going to need to use the quotient rule. So here it is, u prime v minus uv prime over v squared. And like I always do with these, I'm going to set up my old box and ribbon over here. So I've got my numerator, which is the g function, and denominator was the 5x there. And now I've got the derivative of g, which we said earlier was actually f, because if you take the derivative of this, you end up with f of x. And then derivative of 5x is 5. Now, I'm actually going to plug in 3 to all of these things just inside the box before I plug anything in. So if x equals 3, then the following is true. So g of 3, that's the integral from -3 to 3. Now, it turns out we actually already figured that out from part A. If you look back, you'll see that we ended up with 9 for that value. So part A actually ended up being useful when all was said and done. And then for 5 times 3, this is going to be 15 over here. Down here, this is f of 3. Well, that's just f of 3 on the graph here. So looking up the x value 3 on my graph, it looks like I'm down at -2 for that value. And then finally, 5 is just playing itself in this motion picture. So multiplying that out, we've got -2 times 15 minus 9 times 5 all over 15 squared. And we actually don't need to simplify this at all, but we can if we want to. But you do so at your own risk, because if you mess up simplifying it, you lose a point. So just going through here, this is going to be, let's see, -30 minus 45, so -75 over 225. And that ends up reducing by, let's see, 75s actually, to -1/3. For this last problem part, we're defining yet another function, p, as p of x equals f of x squared minus x. And we just want the slope of the line tangent to the graph of p at x equals -1. So essentially, you're asking for p prime of -1. To figure that out, though, we need to talk about p prime of x. So using just our chain rule on this one, that's going to be f prime of x squared minus x times, we're going to have to use the chain rule now because we have an inner function here, so times 2x minus 1. And make sure you use parentheses on all that. At this point, you just have to plug in -1 for everything. So we've got f prime of -1 squared minus -1, all that times 2 times -1 minus 1. So just a whole bunch of writing here. Careful with all your parentheses. And let's see here. So what am I actually plugging into f prime? This is not considered simplified enough because I still need to evaluate f prime of this number. So this is going to be 1 plus 1, or 2. So this is just f prime of 2. Over here, this all comes out to -3. And what is f prime of 2? Well, that's the slope of the f graph at 2, right here. This is just part of a straight line here with a constant slope of -2 if you're going down 2 over 1. So f of 2 is just -2. Multiplying that by -3, if you want to simplify it, that gives us +6.